How's it going, Accelerated Chemistry students? This is Mr. Spurk, and this is your Chapter 14, Section 3 notes, all over ideal gases. So we're going to start with the ideal gas law. Suppose you want to calculate the number of moles, which we denote as N, of a gas in a fixed volume at a known temperature and pressure. The volume occupied by a gas at a specified temperature and pressure depends on the number of particles. The number of moles of gas is directly proportional to the number of particles. Moles must be directly proportional to the volume then. If the moles, which we know is a value, tells us how many of something, they must take up some sort of space. They must be directly proportional to the volume. The more moles you have, the more volume you're going to have. So you can introduce moles into the combined gas law by dividing each side of the equation by N. And we worked with the combined gas law in the last section. P1 V1 over T1 equals P2 V2 over T2. So now we're just dividing by N on each side. This equation shows that P times V over T times N is a constant value. This constant holds for what are called ideal gases, gases that conform to the gas laws. If you know the values for P, V, T, and N for one set of conditions, you can calculate a value for the ideal gas constant, which we denote as R. Recall that 1 mole of every gas occupies 22.4 liters at STP. Insert the values of P, V, T, and N into that equation that we just talked about on the last page. When we plug these in, we get a value for R, and this is our gas constant, of 8.31 liter times kilopascal per Kelvin mole. The gas law that includes all 4 variables, P, V, T, and N, is called the ideal gas law. So we have PV equals nRT. And when the pressure, volume, and temperature of a contained gas are known, you can use the ideal gas law to calculate the number of moles of the gas. So let's use the ideal gas law. So at 34 degrees Celsius, the pressure inside a nitrogen-filled tennis ball with a volume of 0.148 liters is 212 kilopascals. How many moles of nitrogen gas are in the tennis ball? So we know that our ideal gas law is PV equals nRT. And the question says how many moles of nitrogen gas are in the tennis ball. So we're going to solve for N. So we're just going to algebraically solve for N. So we would get PV over RT is equal to N. And now we can plug in our values. So we have N equals, our P value is 212 kilopascals times 0.148 liters over our gas constant, which is 8.31 liters times kilopascal per mole Kelvin, times, and now our temperature of 34 degrees Celsius needs to be in Kelvin. So remember, to go from Celsius to Kelvin, we add 273.15. So our temperature here is 307.15 Kelvin. And now we have all our values, and we can solve for N. So when we plug this in and we solve for N, we get 0.0123 moles of nitrogen. So that's how many moles of nitrogen are inside this tennis ball. So let's try another one. So a deep underground cavern contains 2.24 times 10 to the 6 liters of methane gas at a pressure of 1.50 times 10 to the 3rd kilopascals and a temperature of 315 K. How many grams of CH4 does the cavern contain? Now you might be thinking, or maybe a little curious, that our equation doesn't have grams in it. Our equation solves for moles. But what do we know we can use to go from moles to grams? Our key piece is our molar mass. So here we're still going to solve for n, and then when we're finished, we're going to convert our moles to grams. So again, we have PV equals nRT, and we're going to algebraically rearrange this to solve for n. So n equals PV divided by RT. So now we can plug in our values. We have a pressure of 1.50 times 10 to the third kilopascals times a volume of 2.24 times 10 to the 6 liters all over our gas constant 8.31, and that is liters times kilopascal per mole Kelvin times our temperature of 315 K. So when we plug this in and we solve for the moles, we get 1.28 times 10 to the 6 moles of CH4. But remember, the question is asking us for grams. So we have 1.28 times 10 to the 6 moles of CH4, and we're going to use our molar mass. So we multiply by 16.042 grams of CH4 per 1 mole of CH4, and we end up with 2.05 times 10 to the 7th grams of methane. So really, these problems just become sort of a plug and chug. And your units are going to cancel out, and when we get to class tomorrow, we can talk a lot about making sure these units cancel out in the way that they're supposed to. So now we're going to talk about ideal gases and real gases. So an ideal gas is the one that follows the gas laws at all conditions of pressure and temperature. And its particles could have no volume. There could be no attraction between particles in the gas. So remember, from the kinetic molecular theory, the particles are infinitesimally small. They're so tiny that the individual particles don't really have a volume, but it's their movement that causes a volume. And there could be no attraction between the particles in a gas, which was another statement in our kinetic molecular theory. There is no gas for which these assumptions are actually true. So an ideal gas does not actually exist. But they help us predict so many things about the conditions of real gases. So at many conditions of temperature and pressure, a real gas behaves very much like an ideal gas. The particles in a real gas have volume, and there are attractions between the particles. Because of these attractions, a gas can condense or even solidify when it's compressed or it's cooled, which we know because we recently were going over phase diagrams, and we saw deposition, things like that. So real gases differ most from an ideal gas at really low temperatures and really high pressures. This graph below shows how real gases deviate from the ideal gas law at high pressures. So that black flat line going through the center at 1.0, that is an ideal gas. And these lines, the colored lines, are other gases, and those are the deviations from the ideal gas. And notice that they are at very, very high pressures. So in review, when the pressure, volume, and temperature of a contained gas are known, you can use the ideal gas law to calculate the number of moles of the gas. Real gases differ most from an ideal gas at low temperatures and high pressures. The key equation is our ideal gas law, and that is PV equals nRT. Remember the kinetic theory. Ideal gases conform to the assumption of the kinetic theory. The behavior of an ideal gas can be predicted by the gas laws. With the ideal gas law, the number of moles of a gas in a fixed volume at a known temperature and pressure can be calculated, and although an ideal gas does not exist, real gases behave ideally under a variety of temperature and pressure conditions. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry, 2012 edition of the textbook, the resources CD, and pearsonchem.com. Have a good night, guys.